AI Center of Excellence at ZS. ZS is an analytics firm which was founded more than 35 years ago, and we are right now a $1 billion annual revenue company with more than 25 offices worldwide and more than 7,000 analytical professionals. And specifically, as part of the Center of Excellence, I focus on AutoML, natural language processing, and longitudinal customer journey modeling and customer experience modeling. In addition to that, our COE works on AI areas like small data AI, explainable AI, causal AI, and operationalization of AI, which are the frontier and emerging topics in AI. If you're interested, we are hiring AI researchers, so do feel free to reach out to me. My contact details are right there on the left. So with that, let's jump into the topic for today, which is around customer experience. So as you all know, customer experience is increasingly important, and it evolves through the course of a customer's journey, and which is understood through the interactions the customer has with the various channels and various promotional offers and so on that they are bombarded with these days. And particularly with the digital channels coming up, the personalization and thereby closer management of customer experience is even more critical. So you can see as an illustration here, if we take telecom, each of these three customers, the journeys could be different in the context of, let's say, an international travel planning. There will be some set of interactions before the international travel where they have to figure out how to activate or purchase a travel pass. And after the travel, they come back and there will be some elements of the journey still left out. Maybe they got alerts of how they used, and some of them got bill shock. Some of them faced issues during the course of the travel, and they had some customer call center complaints and so on. So some of them are happy and some of them are not. And the idea is, how can we mine this information, there is rich information, to ensure that we are able to maximize the customer experience and make the experience much smoother for everybody. As I said, there is rich data captured for customers along their journey through the interactions, which is good and is desirable for us to be able to better understand the journey. But at the same time, it poses challenges because there is so much information, both in terms of the volume as well as the high dimensional nature of the data. So if you see the illustration here, a sample customer, each of these points along the timeline is an interaction the customer has. Now that in itself, the number of interactions and the temporal nature of them in itself is introduces complexity, but within each of these interactions, there will be more data points. For example, if the first one is a website visit, now that in itself, there may be the click-through or the click-stream data that we track, where we can see which pages the customer is going through. Did they do a search? Did they interact to a chat window in that? Did they make a purchase? And all these are valuable data points for us to infer the intent of the customer, and we can see whether their intent was addressed within the website or if they had to go to a call center and make a call and so on. Similarly, if you look at this example, there is a call center call. Each call again has a lot of information, both structured, like how many IVR levels did the customer step through, how much time did it take for each of those levels. But in the end, if they manage to talk to an agent, the transcript of the agent of that conversation in itself can have lots of critical information that gives us idea about whether the customer's query has been answered, whether the customer was satisfied or more frustrated, and so on and so forth. So there is so much rich information, but at the same time, this introduces complexities in terms of the computational cost that is necessary to process these, as well as the algorithmic sophistication that is necessary to mine this information and extract insights. And if you look at the conventional approaches that are used to understand the customer journeys, one approach is the qualitative insights, which is typically market research and survey driven. There we typically have to figure out what we are looking for upfront and ask those questions. And even then, there will be limitations like the number of customers you can contact and get direct information. The samples are often very, very small, and you can't capture temporal data because you don't have the longitudinal information and so on. But these are highly interpretable, and you can directly ask questions like, why do you make such a decision, so and so, and you can very readily get the answers. The other approach, which is secondary data-based, is heuristics-based approaches, where you come up with various data explorations and data mining methods to generate Sankey charts, to generate transition probability matrices across the different states, and so on. So this addresses the complexity to some extent, but this also doesn't capture the temporal aspects and the contextual aspects and the longitudinal aspects and so on. So they are also limited that way. And the emerging methods, which are more and more increasingly in use, are the AI-based approaches, which actually capture all of these in much rigorous way. The interpretability, however, is a little bit of a question mark. That's why it is a faded tick mark, if you see. That is because AI approaches, especially the ones that we use to handle these kinds of data sets, tend to be black box models. So there are post hoc explainable AI techniques that we can use, but those are approximate in nature. So that's why it is not completely blank. We do have some ways to do visualization and understand how AI is making decisions. Although approximate, it will still be super helpful. So given these benefits compared to even the slight limitation in terms of interpretability, that is why we see AI approaches being increasingly used to model customer journeys to eventually improve customer experience. So if we look at the framework of journey modeling, if you will, there can be broadly two approaches, right? So one is with an objective to predict something. And when we say we want to predict something, then we are clear with what we want to predict. So it's a defined outcome, it's a known outcome and so on. And we are just trying to predict and refine my tactical execution or inform my tactical execution, sometimes real time and sometimes on a with some lag, a few hours or 1 day lag, so I can be providing timely support to the customers. The other one is with an objective to discover what is happening. This generally happens once a year or twice a year, or whenever there is a key milestone for a particular company, where they want to look at the macro picture and try to understand what are the different patterns. And then if there are some new emerging patterns from that, then if they have to design a new kind of intervention, or if they realize that there is a new kind of customer segment that is emerging for which they have to develop a different strategy, all those kinds of strategy questions can be answered through the discover kind of approaches. So the use cases under the predict are essentially around the key events of customers, like how do I get the likelihood of acquiring a customer? Or once I have a customer, what is the likelihood that the customer can buy a cross-sell product or an upsell product, or what is the likelihood a customer will churn? Which are very important questions. And then some other tactical things like I sent which is the right channel to reach out to this customer out of my, let's say, a dozen channels that I have, or I have these 50 promotional offers, which of them is the best one that this customer will engage with. All these are prediction based questions where I know the intervention. I'm just trying to figure out who will respond best to it and trying to target that. The methods that are used are supervised learning approaches. It could be we do some feature engineering manually, or there are some auto feature engineering approaches as well. And on top of it, we apply supervised learning methods like gradient boosted machines. And these work quite well. Alternatively, we could use deep learning approaches like recurrent neural nets that are using long short-term memory, LSTM, or we could treat the customer journey as an image and apply convolutional nets and try to extract results from that. That is typically more suitable when you have too many customers and you have to parallelize and you want to get computational efficiency that way. And more recently, there is a school of thought to treat customer journey as a text and apply language models like transformers. And we have applied that, and we are seeing really good results from that, even compared to other deep learning methods. So the methods will evolve, but this is the current state that you can see in most of the cases. And Discover, as I said, because it is more of understanding and there is no set objective upfront. So this requires unsupervised learning methods like clustering and attribution analysis and modeling around that. Now, in both these cases, we can actually augment them with some representation learning techniques like autoencoders or denoising autoencoders, and more recently, something like a Hawkes process where you feed the sequence of events and then it will actually see what is the intensity of contribution of a particular event to what we are trying to do in the end. And based on that, you can actually identify the subset of events that are relevant for your problem and only use them. So that significantly reduces the dimensionality that you have to include in the modeling. So broadly, these are the approaches that we use for prediction and supervised learning approaches for informing tactical execution, and then unsupervised learning based approaches to identify the patterns that are happening at a macro level to inform strategy. Now, what we have done is, like I said, we can have this representation learning, and based on top of that can be both supervised as well as unsupervised. We came up with this unified modeling architecture that can support both predictions and discovery. Effectively, I take the sequence of customer data, and then I can actually merge along both the, I can create embeddings for each of the events. I'll show you how they look like, and then the time separation between them. So we are capturing the temporal aspects as well. And then we can actually train an LSTM that will eventually predict what is the immediate next event. And that becomes a representation for every journey. Now, at that point, you can actually take that journey representation and then do the clustering that will inform discovery. Or you can actually take that representation and build a supervised learning model on top of it to predict specific events. And then you can actually inform specific tactical executions based on it. So this kind of a unified approach will actually introduce tremendous flexibility, so that even if you discovered something through clustering, you can very easily pass it back to the same architecture instead of having to define a completely different model for it. So let's look at an example where in the context of telecom, we have actually built a model like this for predicting customer experience. Here, we were trying to predict which customer is likely to call at the call center. And the objective is, to the extent possible, let's preempt the call if we are able to predict the customer about to call. And in case we can't avoid the call, at least can we present all the necessary information to the call center agent in a timely manner, so we are improving the chances of the so-called first call resolution, so that the customer doesn't have to call again and again. And that significantly reduces the cost of call operations, as well as the customer experience will be significantly improved if they are able to find the information without having to call, or they are able to get their questions answered in the first call itself. And how does it look like? You can see that there will be sequence of these, and those sequences will be fed to the deep learning model that we have. The architecture looks like the previous slide. So the sequence could be, for example, one customer had done mobile search, then had to call, then they actually traveled. Afterwards, they had to call. Because they had to call so many times, this is an unhappy customer. Whereas, according to this, because in this case, calling is indicator of unhappiness. Whereas, if you look at the second case, there is the customer did search and search again in mobile, but then eventually did web search, and they made the purchase and did the international travel. So that's a happy customer, because their intent was addressed in the without having to call itself. So how can we introduce a model in between that can actually infer the customer's happiness or unhappiness based on the sequence? So once we built our model, what we have seen is the way it can be implemented is, as the customer interacts, we can calculate the expected satisfaction, which in this case can be measured as NPS. In the customer's profile also plays a role along with the interaction. So we can see that. Okay, I'm seeing some questions, but I would imagine we'll take those questions in the end. So I'll continue for now. So the customer's profile itself will actually play some role. In this case, for example, this is a high LTV customer in a certain age group and using iPhone. So they're generally these kinds of customers, based on the data, they tend to be close to happy, not significantly happy. So you can see that below the bottom line is unhappy, in between is they are neutral, and close above the top line is happy. So these are closer to happy. That's a neutral state. But then as the sequences happen, let's see what's going on here. Okay. Yeah. So the customer in this case has done some web search and not able to find the information. Eventually had to chat with the agent in the website. So that reduced the happiness a little bit, and then eventually had to call. But then their query was answered in the call, so it was a very smooth experience. So they came back to their original state. Then they traveled, but after that they got an alert which potentially showed some bill shock. They immediately logged into the website, did not get the answer. They had to call the call center, and was not resolved in one go. They had to call multiple times, and as they had to call again and again, the satisfaction fell down significantly. So as the sequence is emerging, because we have the model can actually predict what is the likely satisfaction level of the customer. And then we could have, based on this model, intervened right at that time, because now we know that the customer is likely to call next. So you have to intervene right away, and the customer is on the website and not getting their questions answered. So either you can prompt a chat in the window, or at least if you can't avoid that first call, you could have actually armed the call center agent with the necessary information about the travel and the usage and so on, so that the customer didn't have to call multiple times, and eventually, because the satisfaction is so less at the end, we risk losing the customer in the end. So that's how the prediction setup works. Now, at the same time, like I said, the pleasant side effect of this is we can also organize the information that we have in this process, because as we do this, we have to project the high dimensional data. In this case, we'll have lots of events like calling. Is it a general call to the call center, or is it a call about the travel pass? Is it a message in the app, or is it a bill related alert, or is it a mobile app interaction, or is it a website interaction, and so on and so forth. Each of these, again, will have subtypes within them based on the content, etc. So we can actually now see that all of these are very nicely clustered. So all of these behaviors are captured as they are similar. So that will also help us, especially with the discovery process, where which of the things are actually commonly used. And we can also draw relationships between these two on how the customer's preferences, or what is the sequence of choices of these things for a given customer. And based on that also, we can better anticipate what the customers are looking for. Now, we have seen the telecom example. If you look at a similar example on the healthcare side, but this time from a discovery angle, there is always an interest in the healthcare side to understand what are the different pathways that patients go through. And these pathways will involve going through, this is the snapshot for a single patient. There will be some treatment-related interactions or visits, like doctor visits and going to pharmacies and so on. There could be some hospitalizations. There could be tests the patient takes, or diagnosis of various conditions the patient is diagnosed with, and there could be some comorbid conditions also the patient goes through. So there are lots of such things, and there is a sequence of these, and a lot of them happen together as well. There is so much dimension. So one of the objectives for us is to see which of these are really important for me, so I can reduce this dimensionality. Then the second is, what are the distinct pathways, and if different patients are following different pathways, possibly because their profile is different, their comorbid conditions and their setup is different, the managing doctor is different, etc. So based on that, we can actually formulate strategies on how to reach each of these patients separately, how to get them on the right path that will maximize the best outcomes for the patients overall. So the first step is, like I said, we use, in this case, like a Hawkes process that figures out which of these interactions are actually having a different intensity for the eventual event of interest. In this case, let's say an outcome like hospitalization, etc. And then we can only filter for those events. So you can see the Hawkes process will look at the excitation of each of the events as they happen on the timeline. And we'll see which events lead to this temporal intensity spiking. And only those events can be considered for the eventual modeling. So that reduces significantly the number of events we have to consider. And then we can train autoencoders on the remaining data. And then we can actually get some clustering that output will look something like this. So this can be an intimidating chart, but if you see, each of these columns here is a cluster of patients that we identified. And each of these images here, each line here is a patient, right? So a column here is that cluster of patients, and you can see visually that they're all following one kind of pattern. So the first one is they are stable on brand one. Brand one is one type of medication. The second one is they are somewhat stable on brand two, but they initiated on it, but I think some of them are actually eventually switching. The third cluster seems to be switching quite a bit, and there is no specific brand preference in that. And cluster D is stable on brand two, and E is stable on brand three. But eventually switching some of them. And then in this case, this was for brand one. So brand one was interested in, hey, who is actually switching from my brand to others, and what are the different paths that are that they are taking, and what can I do? And depending on how exactly they are switching. So if they are, for example, cluster C, where they're switching to any brand regardless, then my approach to them has to be different from if they are switching from my brand to someone else in different patterns, then my approach to them has to be very different. So I can now formulate my strategies for each of these groups differently. That's the overall idea. Now, we have seen these methods, and we, as I mentioned, we have seen examples in the telecom space, and we have actually applied it on several prediction problems in the telecom, like customer churn prediction, acquisition prediction, upsell, cross-sell prediction, and even the overall call prediction, and so on. And even on the healthcare side, I have shown you examples of how we can formulate strategies by looking at distinct pathways that patients follow, and so on. But these are essentially applicable to any industry, as long as the data around customer journey is captured and the nuances around data and all that are same. Now, what else is needed along with the methods that we have? I think there is still a need to further make progress in explainability. Like I said, we have some methods through visualizations and some of the interactive charts that I have shown that as the sequence is emerging, we can try to figure out what is going on. But there is still a need to look at what combinations of dynamics are actually driving the output, not just the approximate methods. We need to get even better at that. So there is a need for increased emphasis on explainability. And especially this becomes important in some industries like healthcare and financial services, where there is the explainability, even if approximate is not sufficient, we need to be doubly sure that the decisions made and the predictions are not driven by any bias. Now, coming to bias, that often will be surfacing in terms of the data. Either some transactions are missing or some information is missing, and that results in the model being biased, and some of these models actually amplify data biases. So it is important to make sure that the models and the algorithms we build, they are actually robust to these data nuances. So that would mean we have to proactively do some adversarial testing in the data, and we have to do some counterfactual testing as we release this to make sure that there are no biases, to ensure that there is fairness and equal opportunity to all the customers. And the next one, and this is also on the frontier, is so far all the methods that we have seen, they're pretty good and they give great accuracy in doing the predictions, but they're all still based on associations or correlations in the data. They're not necessarily inferring the causal dynamics across the different events. So there is a lot of research that is happening right now on combining causal inference with machine learning, so that can I infer the causal structure automatically based on the data, and then eventually I can be sure that I'm not getting any spurious correlations attributed to the outcome of interest, and that way my predictions are also much more stable. And if the causal structure is actually properly understood, then even if I have less amount of data, I will be able to better define the outcomes, right? So those are the frontiers. To sum it up, customer journey modeling is essential, and it is critical to measure and improve customer experience. And then there is rich data, which is good, but it also poses challenges. There are AI approaches that support a unified solution architecture that can handle both prediction and discovery. And we have seen multiple use cases that actually have been implementing these. And the next frontier lies in improving the explainability, robustness to data nuances, and introducing causal inference.